This is problem 1 on practice exam 7 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. So in section 2.5 of this chapter, we investigated speed versus time for an accelerating Tesla P90D. This gives the rotational rate of the tires during the acceleration. Omega is the symbol for angular speed, so degrees per second, radians per minute, revolutions per minute, which is what RPM is here. So this is the angular speed of the tires as a function of time as it accelerates from rest. Part A, what is the rate of change of the angular speed of the tires as a function of time? Since the car is accelerating, the angular speed of the tires will be getting bigger. So what is d omega dt? Let's start there. So there's rules for taking the derivative of a power, and you can follow those rules to get the answer. We're going to derive it. The normal equation is that this gives the angular speed of the wheel at any time t. Sometime later, dt later, the angular speed is increased by d omega. So the derivative gives the relationship between dt and d omega, and this is what differential calculus is all about, getting that relationship. So we change omega, or omega is changed by d omega when we change t by dt. So squaring that out, and we can throw away the dt squared right here. It's infinitesimal compared to dt. This leaves this equation, and we can see where the omega is. We subtract the omega from both sides, and we get this, and that is the derivative of omega. That's d omega. So we can get the slope by dividing both sides by dt, and there's the slope at any t. If you want the slope at any t, we plug in t right there, and we get the slope. At 4 seconds, we just plug in 4 seconds, and we get 207 revolutions per minute each second. The rate of change of the angular speed, 207 revolutions per minute every second. So part B asks us to check our answer at 4 seconds, and we're going to use a dt of 100th of a second. dt is in quotes there because dt should be an infinitesimal. So there's the slope. We expect a change of, there's the rate, dt is 0.01, so we expect a change of 2.07 revolutions per minute in 100th of a second. And we can use the normal equation to get the revolutions per minute at 4 seconds and at 4.01 seconds. So at 4 seconds, we plug in 4 seconds for the normal equation to get the rotation rate, 1,028.00 revolutions per minute. Now we're going to get it at 4.01 seconds. Using the normal equation, we plug in 4.01 seconds, and we get 1,030.07 revolutions per minute. At 4 seconds, it was 1028. So the difference is 2.07, and that's exactly what we got with the derivative. On to part C. How long does it take for the tire to make one rotation at 4 seconds? So the angular speed of the tires at 4 seconds is given by the normal equation. We can plug it in. We calculated it already, 1,028 revolutions per minute. And we want the time for one rotation. So the definition of angular speed is d theta dt, where theta is the angle. And one rotation is one revolution. So 2 pi radians, 360 degrees. We have revolutions per minute here, so we're going to use one revolution. And that is 0.00097 minutes, which we should probably get into seconds. It's about a 17th of a second. That's part C.